Hello, good morning, or whatever time of the day it is at your place. Thank you for joining today's stream. Um, Today we're gonna do day 10 of Advent of Code. We're almost halfway in, which is really exciting. Yesterday we solved the puzzle on board of the airplane as we were on board our second flight. We started on top of the mountain, went down the toboggan, boarded the airplane at the airport, went to another island and transferred to an international flight. And now we're on day 10, and it seems that we are still in the flight aboard the airplane. So we're going to have to solve another puzzle where the story goes. The setting for that story is gonna be in the airplane. If you have, I'm gonna, as I do it every day, I'm reading the puzzle out loud, thinking out loud as well about the potential solution that I come up with, and then I'm just coding that. If you have any questions at all, feel free to ask in the chat. Hello, Lars. Hi, nice to see you here. Great to have you. I assume you've done the challenges, today's challenge puzzle already. You've solved it. How did it go? When did it go right? Was it tough? Was it a tough one? I already have my code set up for today. I copied the setup code from previous day, which is just reading the input, and then the solution for the first part it's gonna go in here. Oh, you haven't done it. That's unusual because you usually do it before me in the morning. So perhaps you're gonna do it later, or oh yeah, okay, good. Well, yeah, well then, glad to have you here, and hope you get some inspiration from my solution that I come up with. Okay, day 10, adapter array. Let's read these stories. These stories are so fun every time. I really love that you don't just get a puzzle with input and here solve it, but there's also kind of like a behind story as well, and why you need to solve a puzzle that gives you, like, as you progress through the story, which is really adds another dimension to the challenge and makes it really more fun and interesting. So yeah, adapter array, then day 10. Patched into the aircraft's data port, you discover weather forecasts of a massive tropical storm. Oh, that's not good. Before you can figure out whether it will impact your vacation plans, however, you decide your device suddenly turns off. Its battery is dead. You'll need to plug it in. There's only one problem. The charging outlet near your seat produces the wrong number of jolts. Always prepared. What are jolts again? Is it volt? Oh, I think jolt is made up. Okay, I think it's equivalent of volt. Always prepared, you make a list of all of the voltage adapters in your bag. Okay, each of your voltage adapters is rated for a specific output voltage, your puzzle input. Okay, so the puzzle input is the adapters that I carry with me, and they are work with a specified output voltage. Any given adapter can take an input 1, 2, or 3 jolts lower than its rating and still produce its rated output voltage. So we have a margin of 3 on the lower end. In addition, your device has a built-in voltage adapter rated for 3 jolts higher than the highest rated adapter in your bag. So if your adapter lists were 3, 9, 6, your device's built-in adapter would be rated for 12. So it's what your device has a built-in voltage adapter rated for 3 jolts higher than the highest rated adapter in your bag. Okay, makes sense. 9 is the highest, therefore our built-in is 12. 3 plus 9. Treat the charging outlet near your seat as having an effective voltage rating of 0. Since you have some time to kill, you might as well test all of your adapters. Wouldn't want to get to your resort and realize you can't even charge your device. No, definitely not. But we're going on holiday, so we maybe should be offline. If you use every adapter in your bag at once, What is the distribution of voltage differences between the charging outlet, the adapters, and your device? Oh, I don't get this. Let's see if the puzzle example gives me a better clue. For example, suppose in your bank you have adapters with the following voltage ratings. Okay, 16, 10, 15, so on. With these adapters, your device's built-in voltage adapter would be rated for, we get the highest number, 19, plus 3, 22. Okay, 3 higher than the highest rated adapter. Because adapters can only connect to a source 1 up to 3 volts lower than its rating, in order to use every adapter, you'd need to choose them like this. The charging outlet has an effective rating of 0, so the only adapters that could connect to it directly would need to have a voltage rating of 1, 2, or 3 joules. So you can also go higher. Oh yeah, higher. You have to go higher. Of these, only one you have is an adapter rated 1 jolt. Okay. From your 1 jolt rated adapter, the only choice is your 4 jolt rated adapter. Okay. From the 4 jolt rated adapter, the adapters rated 5, 6, or 7 are valid choices. Okay. What do we do then? However, in order to not skip any adapters, you have to pick this adapter rated 5 joules. Oh, so you have to use them all? If you use every adapter in your bag at once, what is the distribution of voltage differences between the charging outlet, the adapters, and your device? Oh, I see. So you have to use all the adapters possible. So then we use 5, and then we use 6, and then 7. And then we proceed with 10. And then we can choose between 11 and 12. So we choose 11, then 12, and then we go on with 15, then 16, and then finally your device's built-in adapter. Oh, and then 19, yeah, and then finally your device's built-in adapter is always 3 higher than the highest adapter, so its rating is 22 joules. Always a difference of 3. That's good to remember. In this example, when using every adapter, there are 7 differences of 1 jolt and 5 differences of 3. Oh, I see. So it makes like a string of connected adapters, and then you calculate the differences between each of them, and then you add them together. Is that correct? 7 differences of 1. What's the question? Oh no, you don't need to add them. You need to multiply them. Here's a larger example. In this large example, in a chain that uses all of the adapters, so it's a chain that you create, there are 22 differences of 1 and 10 differences of 3. Find the chain that uses all of your adapters to connect the charging outlet to your device's built-in adapter, and count the voltage differences between the charging outlet, the adapters, and your device. What is the number of 1 jolt differences multiplied by the number of 3 jolt differences? So that's going to be our answer. Oh, interesting problem today. I think I just get confused by, the puzzle input is not that big at all. I think I just get confused with the terminology, the voltage and device and outlet, and not being a native, kind of like need to think twice about what is exactly going on. But so I saved the input in my working directory. I'm going to get rid of the last line here. Let's split this to the right. Split right. Okay, we can get rid of the sidebar. Let's make the code line a bit bigger, actually. Here. So we can look at our input while we solve it. Okay, so we have our input, which is a bunch of adapters, and we need to figure out, well, well, first of all, we need to create a chain of them. So we need to start lower and go higher. And then I think we have to use them all. We go higher, and then when we reach the end, we also use our own device, and then we have to calculate the differences between each chain item, kind of. And we take the number of 1 jolt differences, and we multiply it by the number of 3 jolt differences. I don't know, I just came up with like while I was thinking out loud, I think if I just first split the input into with new lines, so then we get an array of elements. And what's an individual is an adapters. Okay, so we can call it adapters is equal to input split new line. So we have our adapters array here, and then if you can just sort them, and let's sort them by well, let's sort them increasingly from lowest number to highest number. And then, well, what are we finding out? Okay, we need to find out like a number, so I'm just gonna say const answer part 1, and we're going to use reduce eventually. But maybe not yet. First we need to find out, well, let me just console log. Well, I'm gonna try and not use console log as much as I can, and just have use the debugger. It's more convenient if you get used to using the debugger and you're pretty useful with it. It's pretty powerful tool. So answer part 1 is undefined, is it? So we get our adapter. Oh, okay, so here's our input and it's sorted. Why is it wait, so it's sorted. Oh, I need to map those because they're numbers, so I need to typecast them from strings. Let's do that. There we go. This is just a shorthand for passing in the argument of map to number. You can just pass the function and it'll go directly. Okay, let's give it another spin. Okay, so, well, we want let's I don't know if I can add a breakpoint at the end of the file. No, not really. It needs to do something. I'll just put an empty console log in here. Okay, so we have, wait, still not working. Console log, maybe it's erroring out. Oh wait, breakpoint is at the wrong line. There we go. So we have an array of numbers now, and it's sorted. I think this is looks pretty straightforward. We just go through the array, and since we know it's a given that we are able to use all the adapters with our input, so there's not going to be any adapter here that's outside of, so we can't link them from beginning to last. So there's going to be like 4 joule differences. That's not going to exist. The differences between each adapter is going to be either 1, 2, or 3. We can quickly verify that. 1, 1. This is 3, 1, 1. Let's see if you find 4. I can't seem to find 4. I think that's kind of like implied from the puzzle that you should be able to string all the adapters together in one long chain. And it seems like it's indeed the case. And then our own device kind of comes in last with +3. So on device's voltage is 162. Yeah, that looks right. So then we have this array. What we can do is we use reduce, and we need to return a number. So we can like say, well, I try to avoid ACC as the variable name for reduce, even though it's kind of like, hi Chris, glad to have you here, welcome. Chris is using the party, well, he's using the corgi emoji with kind of like rainbow colors, which is associated with the party corgi Discord. It's a really fun community of creators and programmers. Wait, I spelled this wrong. Here it is anyway. I definitely recommend joining to let's just hang out and talk about anything web or anything at all. Here's the website. I'm gonna link it to the chat, and you can click on this invite link. I always hang out in there. There's a lot of streamers there too, so it's nice to see what other people are streaming about. And Chris himself is streaming Advent of Code as well every day, and he's doing them in Rust. So if you're learning Rust or just curious about how a different person comes up with today's solution, do check out his stream. His stream is usually a bit later in the evening, European time, which is afternoon, morning if you're in the US. My day 10, thanks for asking. So far so good. I have this console here. What I'm doing now, so I have the adapters sorted. You can see it here. I have the adapters sorted. I typecast them to numbers from strings, and I have them sorted. And so I was just going through the array and like figuring out whether there's a chain so I need to. The puzzle goes that I have a bunch of adapters with me, and I have a device. I'm still in the airplane, by the way, second flight. So I have a device on me on the flight, and I need to charge it. The battery is empty, and there's an outlet that has a voltage, not a voltage, voltage of 0. And the rule is that you can only connect the device or an adapter to the outlet if it's up to 3 higher voltage than the current output. So the outlet has 0 output, and I have a bunch of adapters with me, which is the puzzle input. And these, each adapter has a voltage value. So I need to kind of like the puzzle input asking me to create a chain, or using all the adapters that I have with me, and including my device. And the device's voltage is 3 higher than the highest adapter that I have with me. And then the answer to the first part is going to be the number of 1 joule differences multiplied by the number of 3 joule differences. So that's the puzzle for today. What I have so far, I've sorted the array. So since I need to create a chain anyway, this is kind of like the chain already made for me. And I know, given from the puzzle story, that I'm going to be able to use all the adapters. So there's no 4, 5, or anything higher than 3 joule differences between any 2 elements in the array. And our own device's voltage is going to be given this input. It's going to be 159 plus 3, 162. So now I'm using reduce, and I need to come to kind of like compute the answer from the array that I have here. And I just thinking about what to name the variable. It's kind of like common practice to name it ACC, kind of like, which stands for accumulator. I do try to avoid this though. It's like the number of 1 joule differences multiplied by the number of 3 joule differences. I can just call it answer part 1. That's good enough. And then here we're gonna have our adapter, and you know what would be neat? If I have this array, if I kind of like map this array to only have the differences. But then I can't use map because map always returns the equal number of elements, and the difference is going to be 1 element smaller, less, because we're only looking at differences. But we have the last difference though, which you can add to it. Yeah, we could do that. Let me see. I think we could do that. I think we can say, hey, the first element is going to be the difference between the first element and the second. The second is going to be the difference between that one and the next one, and so on until we reach the end one, and the last element is going to be the difference between this one and our own device. So I think we can do that. Let's use another map in here, and it's going to say adapter. All right, and then we return. Let's also grab the index because we'll need the second, and I'm gonna use the array here because we're gonna need to tap into the element following the current one. So we can say adapters index if the next adapter. So yeah, the next adapter minus current adapter is gonna give us the difference, which we can just boil it down to a one-liner. Yeah, so then we should have our differences. And then we can just so our answer is going to be the number of 1 joule differences multiplied by the number of 3 joule differences. I could create an array. Two arrays, because I would like to see what I'm working with at this point in time. So I think we can let me look up reduce. I think we get the array as the 4th element. Yeah, so we'll have index adapter differences, kind of like it's adapter, or no, what do they call it in the puzzle here? Joltage differences. Okay, jolt differences. Okay, jolt differences. Okay, that's good. And I'm gonna add a breakpoint here. We're using the debugger. I started using it for the last few days of advent of code. Makes it much easier. Okay, so something's definitely wrong in our second map function, because we have a bunch of 0 differences, which shouldn't be right. Adapters index, of course, index +1. It's always the small stuff that gives us bugs. Okay, so we have joule differences. Okay, so we have a bunch of 1s and 3s in here. Oh yeah, and the last one is not a number, so we'll need to account for that as well. If adapters dot length, if index is if we reach the last element, so then we say if adapters dot length equals index, then return for a fact, I know that's 3. I can just hard code it because we sorted the array. The last element, meaning the last element is going to be out the adapter with the highest joltage, and we know from the puzzle input that our own device has the joltage of the highest adapter that we have with us plus 3. So we can hard code this. It's not going to vary it given a different input. It's always going to be the same. So let's run it again and see how our array looks this time. Still not a number. Adapter's length equals index. If it does, return 3. Otherwise, return a difference. This looks good. What have I done? Adapters.length. Am I off by 1 here? If the array has what, 97 elements, so the index is going to be 96. Oh, I see. Off by 1, I guess. Still our number. Is equal to index minus, no, not -1, +1. That's why I dislike imperative programming. If you have to tap into, figure out like, is it +1, -1? Okay, there it is, 3. I'm not sure if I could do this with functional in here. I guess I could also just say, if this exists, if we have an element here, then return that element, or like the difference, otherwise return 3. Perhaps this is easier to wrap your head around. Yep, still works. Okay, I'm gonna stick with this. Okay, so we have a bunch of differences that we now need to figure out how many of them there are in terms of 1s and 3s, and I can only see it's 1 and 3. There's no 2 differences, although the puzzle input does not say that there cannot be 2 differences. There can also be 2 jolt differences. So let's not assume that given our input that it's only 1s and 3s. We'll need to actually verify that. But then we need to multiply the sum of 1 jolt differences with the sum of 3 jolt differences. So what I'm thinking of right now, we have an array. We could, what's like the easiest way to do this in code? We could filter the array 2 times and kind of like create 2 separate arrays, one with 1s and one with 3s, and get the length of those 2 arrays and multiply them together. That's gonna work. But then I'll need to refactor a little bit, because I need to assign whatever is after this line to a variable and then use the same variable twice to get 2 arrays, because I can't do it in one go. I'll need to do it in two loops. Let's see if I can come up with a different solution that does not need me to refactor that. Can I calculate this trait using a reduce? I'm sure it's going to be less readable. Of that, I'm sure. But we're optimizing. I said to myself, in this advent of code edition, I'm going to optimize for readability and functional programming. So I'm going to go with the solution I came up with right now. Yeah, I'm going to have 2 arrays. So let's rename this variable to be sorted jolt differences. There we go. And then we can get rid of this. And then we can say here const 1 jolts differences. And that's going to be sorted jolt differences filter jolt difference. I always err on the side of, when naming my variables, I always err on the side of being too verbose than being too clever and short. Characters are cheap. They don't cost anything. We're writing code for humans, not for machines. So I don't mind having a bit of like long variable names as long as they like make the intent clear, make it clear what they hold. So jolt difference, if jolt difference equals 1, then we have our 1 joule differences, and then we're gonna wait, nope, there, and then if it's equal 3, then we have our 3 joule differences. So our answer to part 1 is going to be let me quit the debugger, it's kind of messing with me here. Console log answer part 1, 1 joule differences dot length multiplied by 3 joule differences dot length. Does that look okay? I think it does. It's pretty short solution too. How long did I take it? It took 30 minutes to write it. Should have been shorter, but it's because I'm explaining stuff, so that's fine. Let's go ahead and run it for the first time. Run our solution for the first time and see if it's correct. We do get an output. I'm gonna just fill it in and see if we're on the right end here. Not the right answer. Your answer is too low. Okay. So we need to have a higher answer than we do right now. 2080. What's the, let me read the question again. What is the number of 1 joule differences multiplied by the number of 3 joule differences? And we also include, could I just, what I'm gonna do is I'm gonna use the example puzzle input as a new file, input.txt. Oh wait, let me rename this quickly. Or I'm just gonna create a new file. I'm gonna use the example input to kind of like test my program. So what do I get given this input? I get 210, and here we have 22 differences of 1 joule, so that's 22 times 10 differences of 3 joules, so it should be 220, and our program gives 210. So that means we're missing a 1 joule difference because we're doing 21 multiplied by 10 instead of 22. So we're missing a 1 joule difference. We might be off by 1 somewhere here in our program. Let's use the debugger, and I'm gonna add a breakpoint here, and I'm gonna add another breakpoint here. So we have the adapters. Oh, I see. It's using the original array and it's not using the mapped array. I wonder if map, so map doesn't give us, it gives us the original array it was called upon, not the one we're working with. The array map was called upon. Well, it's chaining, so it should be, because these are strings, these are numbers, and I'm already typecasting them here. So that's, I think, where we are but why is index? Oh, because we're not, yeah. Can I add like another breakpoint here? I can. Okay, so what's get rid of this. Let me put this a bit more to the side so we can see the whole code. What's adapters now? Oh, it's numbers. Okay, so it didn't execute yet. Good. So it's numbers. That what's index should be 0 plus 1, so we get the next one in line, and then we get the current adapter, which is like 1. Otherwise, it's 3. So we have it here, so it's saying like this should be 1, and then 1 1 3 1 1 1, and so forth. And then the last one is 1, like second last one is 1 and 3. So let's remove this breakpoint. And so what do we have here? Jolt differences. This looks right to me. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21. So we are off by 1. Oh wait, I need to calculate the difference between the adapter and the outlet as well. That's what's wrong. Yep. Okay. So yeah, this map is a bit hacky because I'm adding an element at the end, which is the difference with the last one, but I also need to add an element at the top as well, which is going to be the difference between the first adapter and the outlet. So how can we do this in a neat way? I guess I could do it here, and I can say what was the function? Was it push? When you want to push an element into an array at the beginning? Where's this at the end? Push, one more at the end. No, so it's not push. Is it shift? Shift. Removes. No. I know pop also removes, so it's... Oh, forget it. It must be the fourth one. There's shift, pop, push, and... What does pop do again? Removes the last one. Push adds one at the end. Shift removes the first one. I need the last one that adds at the beginning. Where is it? Fill flat. Slice. Sum. Unshift. There it is. Add one or more elements to the beginning of an array. Yep, that's the one we're looking for. So what's we have this array 4 5. Expected output 5. Returns the new length to the array 4 5. Okay, we don't care about that. So it does modify the array in place. That's good to know. Unshift, and then we're just gonna add 1. No, we cannot assume that. We're gonna add the difference between the voltage, between the first adapter, adapters. Yeah, this needs to be. Let me see. You know what I'm gonna do? I'm gonna map this in here. Then yeah, that's easier. So we have a number in here and at the first index, so the first adapter minus the outlet, we add that difference to the so let's run it again. I think now we have one more. Yeah, it's one more. And the length is 32, which is, okay, let's see what our answer is now. 220. Okay, so we get the right answer. Good. Let's test it again with our input. What's the answer we get? 2112. Let's give it another try. And it does work. We got that star for today. Awesome. 19 stars. And continue to part 2. We did it. Pretty short. The solution is not very verbose. It's also, if you read it, it's pretty easy to follow. But it did take me 40 minutes to come up with it. But then again, the length of your code does not imply how much work you put into it. I think it's kind of like writing. Writing short, succinct prose or like articles is much harder than rambling on words for a long period of time. So yeah, I think similar with code. What we did it. Yeah, thank you Lars, thank you Chris. Oh, this description makes me scares me a little bit. Let's read what part 2 is about. To completely determine whether you have enough adapters, you'll need to figure out how many different ways they can be arranged. Oh no, this is gonna be tough. I already can see that. Every arrangement needs to connect the charging outlet to your device. The previous rules about when adapters can successfully connect still apply. So the first example above, the one that starts with 16, 10, and 15. 16, 10, which one? This one. Okay, so from this example, supports the following arrangements: 1, 4, 5, 6, 7, 10, so on. So what happened here? They removed. No, they did not. 19, 16, 15, 12, 11. So they got rid of 11. Where's 11? So you can remove adapters as well. Okay, so no 11 back. 6 got removed here. 6 and 11 got removed. Oh, I see. So you can remove adapters. Okay. As well, the charging outlet and your device's built-in adapter are shown in parentheses. Yeah, so it's 22 and 0. Given the adapters from the first example, the total number of arrangements that connect the charging outlet to your device is 8. So this is the second example here. Okay. So the total number of arrangements that connect to the charging outlet device is 8. The second example above, the one that starts with 28, 33, 18, has many arrangements. So these are 8 and these are many more. And here are a few. So these are not even all of them. Okay. In total, this set of adapters can connect the charging outlet to your device in, oh, that's a lot, 19,208 distinct arrangements. Okay, so the problem with today's puzzle is as well, if you look at this input is not that large compared to ours. Ours is, I would say, at least 3 times larger. This input produces 19,208 combinations. And I think that it becomes exponential. This number increases exponentially as we add more adapters to our input. So our input is going to have somewhere in the lines of a couple of 100,000, maybe a million, several million arrangements. And this might be the first time in this year's edition of Advent of Code where we, if we take a brute force approach to solving this, it might just take a long time for the program to compute a solution. But let's see. You glance back down at your bag and try to remember why you brought so many adapters. Yeah, indeed. There must be more than a trillion valid ways to arrange them. Surely there must be an efficient way to count the arrangements. Okay, so I think the puzzle already tells us that a brute force approach is going to be is not going to do it for today. So you need to find an efficient way to count the arrangements. What is the total number of distinct ways you can arrange the adapters to connect the charging outlet to your device? I don't have a strong math background, so, and I'm sure there's a mathematical approach to taking this, to approaching this problem. And I could Google it, and I could spend a lot of time Googling it. Let's see if there's something I can come up with. So this is our input. So we can sort the array, and then we can let's say we have like a sorted array here. So that's one arrangement, at least the initial one, and then we can remove. We can start removing elements for as long as after removing them, like the difference does not become larger than 3. So we can do one pass and remove each element, and then wait, as we remove one element, we need to find the combinations of those as well. Oh, that's a lot of nested loops. No, I cannot program this. Okay. If you have any hints, chat, let me know now. That would be greatly appreciated. Something that points me to the mathematical, something I can Google at least. I have no idea what to Google. Because I don't think a brute force is going to do this, because I will need a nested array for each combination. It's just a nested loop, I mean. There's a bunch of nested loops. Ain't gonna work. Ain't gonna work. So we have an input, and we need to get like combinatorial. We talked about graphs yesterday. I did, but I did not use graphs. I did use graphs in the day before that. Could I use graphs here? Or is that maybe what you're suggesting, Lars? Let's see. From the chat, Lars says, I'd probably do a graph and count the combinations from that phi traversal. So do a graph and count the combinations phi traversal. So then each element would be, so we start with like the outlet at the top. That's going to be our first node, and then we go down to 1, and that's going to be our second node, a child node, and then 4. Then we're going to have like, thinking about how to create this graph then. And then as we remove, oh no, wait, we can have the possible, so 4, so the children of 1 is going to be 4. Oh, just 1. Okay, the children of 4 is going to be 5, 6, and 7, because all of them are possible children of 4. So then we have the graph for it's going to be 5, 6, 7, and then I append to 5. I append, well, 5 cannot have 10, so that's so 5 and 6 won't have any children. 7 will have children. It's going to be 10, and then to 10 I append 11 and 12, and 11 is not going to have a child. 12 is going to have 15, 16, 19. I guess I could do it like that, and when I have eventually I have like a big graph, and then I'll need to count. So Lars suggests to count the combinations from that phi traversal. So when I create that graph, I can just traverse it, and the number of bottom nodes is gonna be how many possibilities we have. There might be other easier ways, but I like graphs as I can visualize it in my head. I like graphs too. I can visualize them relatively okay, but they're kind of like pretty tough to deal with in code, I find. Traversing a graph, at least for me, is not something I do very intuitively. So thinking about the solution, if I create a graph from our input, It's going to have a bunch of different children and connections to nodes, and then the bottom nodes is going to be, each bottom node is going to be one arrangement that works. Ooh, but building that graph in code is going to be a tough one as well. The number of paths through the graph is number of combinations. Yeah. So it's if I pull up an example graph here, not that kind of graph, this type of graph. So we're gonna end up with something similar to this, but much larger. And then we can, each bottom node, wherever you are, is gonna be an arrangement. So we can go like here, this is one arrangement, go up, this is another arrangement, go up, and here there's gonna be another arrangement, and so forth. So like this particular graph has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 arrangements. Is that kind of like what, yeah, but it's gonna be a huge graph though. Is this, well, I guess it's more efficient than doing nested loops, yeah. All right, yeah. I think this is what I'll have to go with, because I can't think of anything better. I'm sure there's some clever people know that there's a math equation you can use for something like this that makes sense. I'll do some quick googling, see if I can come up with something. Math equation combinatorial. I'm really bad at this stuff, or at math stuff. Yeah, when I see this, this is completely hieroglyphs for me. I have no idea what that means. Number of k combination. I'm sure this, like the math solution kind of like must involve some combinatorial computation, but we'd first need to figure out how many of them there are, though. We don't know that in advance. Yeah, I'm not gonna venture this way. I'm gonna go with Lars' suggestion. I think that's worth a shot. Lars says, so one node per adapter, and they just need to store build the edges. One node per adapter. I was thinking to actually multiply have the adapter be several nodes depending on each path, and then just store build the edges. So I guess that would be more efficient too. If I have one node per adapter here, and then just store. Can I find something that kind of like gives me from array to graph, so that I can visualize this somewhere? A tool, plot graph from array, MATLAB. Nope. I would have wanted to visualize the graph, how it would look like given our input. But let me see, if we have here like 1, 2, and then possible 3, 4, 5, 4, whatnot. No, I don't think that's gonna work, because you need to find out if you. No, I don't see a way how having one adapter per node. Graphviz. Oh, Graphviz might be able to help us here. Let me see. Okay, this is interesting. Start engine Format, okay, doesn't matter. Okay, so what do we have? It's Python. Looks like Python or some else. So what do I do? Oh, okay, yeah. I'm thinking if I have a node for each adapter, how do I know? Like, my question is, if I have, let's say I have like 1, 2, and then 3, 4, 5. Let's say we have a simple graph, and then we have like 5 plus 3, it's 8. So this 8 will only be a child of 5 because it cannot be an adapter for 3 and 4. So that's not a valid arrangement. But what if you have, say, 7? We have 5 here. We can connect 5 to 7, but we can also connect 4 to 7. So this 7, oh, I see what you mean. The 7 is gonna be the child of both parents. Oh, I see. So it's not gonna be, I forgot the terminology for this, but this is like a unit-directed graph. No. So you have a different type of graph where you can have a child have more parents. So this graph, an attribute of this graph is that there's not more than one parent. Each child does not have more than one parent. So kind of like branches off. And you can have different graphs where you can have a different graph with an attribute where childs have multiple parents. And then indeed, I think that's what Lars is suggesting. Then you can just count the possible pathways. But I need to kind of keep track of which edge I went through. But I can just traverse the graph, I guess, from left to right. Okay, so what's here? Another link. Oh, thank you for that. Yeah, I don't know what. Yeah, thanks for creating this. Okay, so this is cool. Yeah, I can work with this. So we have 1, 4, 6, 7. So what I was saying was, like, if I have 1 and then I have 2 and then I have 3 and then I have 4 and like this. So I have, so I have 1, 2, and 3 and 4, and then let's say I have 4 that goes to 6, and then I have another one because 3 can also go to 6. Yeah, so this is kind of like what our graph is going to look like. And then further on we can have like 6 goes to 7. It can like branch off again, and 6 goes to 8, and so on. So for example, if we have this input, this graph, then we have how many combinations? Well, only those combinations are valid that or arrangements that reach the end. So if we move, well, that doesn't make much sense though, because wait, they also need to be interconnected, don't they? 1 leads to 2, 2 can lead to 3, 3 can lead to 4 as well. Something like this. So you have, this is one possible combination. So we need to create edges between all the adapters. Okay, so 1 can lead up to 2, 2 can lead up to 3. No, wait, so 1 can lead up to 2, 3, and 4. 2 can lead up to 3 and to 4. And to 4. Exactly. And 3 leads up to 4 and 6, and 6 leads to 7 and 8. So this particular graph has how many arrangements? Like 1, so you count each path. 1, 2, or 3, because these are 2 possible paths. Okay, so 1, 2, 3, 4. Wait, and 7 can also lead to 8. This is even too complex for like my own head to wrap around. Let alone too many to to count manually already. I'm just trying to get a sense of this because then I can program it. So if we go 1, 2, yeah, that's a lot of them. Let me see. Because I think, so the first challenge is going to be to create this graph, and I think I can pull it off. I think I can do that. But then we get to the second part where I need to kind of like traverse the graph and get the number of different arrangements. And if I can't even do that by like with this small input, then how am I do this in program? So that's why I'm trying to figure out how am I going to code a graph traversal that keeps track of each possible combination. I guess I could, so like 1 goes in here, and this one has 2 different possibilities. So I can have a recursive function that feeds that gets a new copy of a graph and then computes for each one. But that's gonna be, isn't that gonna be the same as doing a nested loop? Or no, maybe not really. I think this is gonna, because you're gonna end up with a lot of recursive functions, a huge call stack. Yeah, because I don't want to commit to like trying to solve this and be like 1 hour in, and then I finally created a graph and I finally done the traversal, only to figure out that the computer is or like my laptop is gonna crash because it takes so long, or the so that's kind of like the thing I'm afraid of before I commit to this, to actually implementing this in code. Is this gonna work? The call stack will max be the number of adapters. Yeah, that's true. I think if we are here 2, 3, 4, and then we say okay, go in here, and it'll go until it reaches the end, and then it'll back off until it goes to another branch, and then it'll go. Yeah, that's true. So indeed, the call stack will not be bigger than how many adapters we have, which is 97. So yeah, I'm gonna be able to handle that fine. Okay, I guess I'm gonna go with this, but I have no idea yet how to do the traversal, but we'll figure that out as we code. Let me pull this up in here so we can visualize it. Yep, okay, I'm gonna get rid of that. Chris says, gotta bounce and get some sleep. Yeah, thank you very much, Chris. Thanks for sticking around. Thank you for sticking around and keeping me company. Get some sleep, and I wish you good luck with your stream and your solution to this today's challenge. Thank you. All right, let's continue on with part 2. This is a tough one. This is the first one so far in this event, and I'm like, ooh, sweating. Okay. We'll need to create a graph. Part 1 was so easy though. Part 2 is like, bam, different level. Okay, let's clean up some tabs here we don't need. We need this one. Okay. We have the sorted array. We'll need the array to be sorted because we're gonna go through it. And then what does it do? The differences. Okay, so we don't need the differences, but we do need to get a sorted array. And then need to build a graph. Build a graph in JavaScript. Oh, never build a graph in JavaScript. Yeah, just gonna go build tree graph in JavaScript. Maybe I can use some function, maybe not. For visualization, let me see. If there's a third-party library that just grabs an array as input and builds a graph for me, I'm gonna use it. I'm gonna cheat on this one and use a third-party library because it's gonna make my life easier. Graph? Anything with graph related? Not GraphQL. Tree. Graph. Build graph JavaScript. Graph library JavaScript. No, that's not what I mean. I mean a tree graph, not a plot graph. Construct tree graph JavaScript library. I always get triants drawing tree drawing. I don't want that. How do I draw a graph for tree structure in JavaScript? Yeah. Okay, so this person has some suggestions. Well, I think this person is asking how to actually draw the graph. I don't need to draw it, I only need to create it. So I can Google perhaps tree graph data structure, because I only care about the data structure. JavaScript. Again, I get triant. Lars says, a graph edges gives me example. Need to be able to find the outgoing edges fast. That's true. That is true. So Lars comes up with let me see. Let's do that in here then. So we have an object. Let's say we have an object. We have let's actually get our input in here. Let's say our inputs 1, 2, 3, 4, 6, 7, 8. Okay, let's say our inputs 1, 2, 3, 4, 6, 7, 8. 1, 2, 3, 4, 6, 7, 8. So this is our input. So let's say then we have 1, which is we have kind of like an object, and then we have the keys 1, and then we have an array of nodes, which is going to be for 1 is going to be 2, 3, and 4, and 4, and then like that. And then for 2 we have a different array, which is going to be 3 and 4, kind of like this. And then as I traverse to the graph, so if I end up with a graph kind of like this, let me continue this a little bit. What is oh, I'm not sure. So if I create a few more examples here, 3 has what? 3 has 4 and 6. 4 and 6. 3 has 4 and 6. Do we go on? 4 has 6. 6 has 7 and 8. Well, this is good. So something, I don't know why it's complaining. Okay, perhaps because yeah, okay. So if I traverse the graph, if I create a graph like this and I have to traverse it, then I just go first property of that object is going to have an array, and then I go for each element in the array, I see if that property exists in the object. If it does, then I go inside it, and I go again. I do that for this. Oh, Siri is turning on. No. Okay, so 3, does 3 exist? It does. Then go to 4 and so on. Okay, yeah, this looks good. So then we're gonna end up with 97 properties, and each is gonna have an array of, yeah, this looks good. Thank you for that suggestion, Lars. This I think is gonna bring us to the right, lead us on the right track. Yeah, it's gonna be indeed quite fast to traverse, and not that hard to make either. I hope. So we have we have an array. We're gonna create an. Okay, so let's have our graph here. We're gonna call it, yeah, graph. Good enough. And then we have a sorted array. So what I want to do is can I do an object? I want to create an object with those. Yeah, let's start with that. I want to create an object with those from an array, from entries. Object from entries grabs. Oh yeah, key values. Key values. Okay. So perhaps I'll need to first kind of like map adapter. So we have our adapter, and sorted. Okay, so we have our adapter, and then we need to, you know what I'm gonna do first? I'm gonna be a little bit smart about this, and I'm gonna say I'm gonna add the outlet and the device into the array, so we don't have to deal with kind of like this again. So then we have a complete array of things. Although, is it relevant for part 2? Total number of distinct ways you can arrange the adapters to connect. Nah, it's not really relevant. No, because we're not looking for the differences. Okay, so that's fine now. We can stick with that. And then we have an adapter. So we need to create an object from entries. We need to have each array be we need to have a two-dimensional array. So we need to kind of like adapter. I'm gonna say adapter node. And then adapter node is going to be adapter with another array inside it, because that's going to be, so this is going to be the key of the object, the property, and that's going to be the value. And in there we need to find, well, we need to kind of like filter possible adapters, and then we need to go through, I mean, I could just, there's only 3 possible adapters, so I could just I could slice the array. Let's do that. Index, and then we have sorted adapters, and I could just say possible adapters. It's not, what do I call it? Possible adapters, children adapters. Okay, this is good enough. Children adapters is gonna be sorted adapters, and then we slice the array so we only look at the 3 following the current one. So that's gonna be starting from index, slice, starting from index plus 1 up until index plus, up until and including, I guess, but not including. Okay, so plus 4. So that's gonna give us 1, 2, 3. That's good. And then in there we do a filter adapter if the difference between, oh yeah, wait, next adapter, if next adapter minus current adapter is smaller than 3 or equal, yeah, smaller or equal than 3, then we have the children adapters, and they are gonna be in here, and it's gonna be an array anyway, so we can get rid of this one. And I think we have our adapter node then, which we need to return. Adapter node. And then from here we say object from entries. Object from entries. Let's console. No, let's. I need to add a console log anyway, because I need this as a breakpoint. Okay, let's run the debugger, see what it gives us. So graph is an object with each adapter as a property, and then that adapter has an array of possible children adapters. So for 1 is 2 and 3, for 8 is 9, for 9 is 12. Okay, this looks pretty good. Did we already create a graph in just 2 lines? Did not expect it to be that easy. But thanks to your suggestion, Lars, because I would have not think. I was thinking of creating a much more difficult graph, kind of like a linked list type of graph. Ooh. But this is much easier if I just have to use an object, not a linked list. Something weird. Yeah, I think we have our graph now. So we need to traverse it. Let's see at the end. So this is the last one, 159, which doesn't have children, so that's fine. We need to kind of like find all possible. Let me think. Wasn't the combinatorial math combinatorial math, wasn't the formula that if you had the number of, let me see, hey, they use graphs as well. Peterson graph. This looks interesting. I need a math formula. Where is it? Combinatorial math formula. Because if you have here it is, total number of objects in a set and the number of choosing objects from the set. I don't even know how to do combinatorial in program, in code. I was hoping to get to just have to do the math and then I have the answer, not and avoiding having to traverse the graph. But I might have to do it anyway. So it's the number of k combinations from a given set of elements. 3 element subsets of a 5 element set. So here we have the input is like 5 elements, and we need to find the possible combinations that have 3 elements. Okay, so that makes sense, but our input is not, our challenge is a little bit different. Where's my graph? Oh, here's my graph. Challenge is a bit different because we don't have, no, because we have, no, it's a little bit different. I don't think we can use this function. Okay, let's traverse it. Let me see. So we have the, for 1, we go inside it, and then we grab the first element. It's going to be 2, and then we find 2 in here. Of course we find it because any element that's going to be in the array is going to be in the here as well. So that's like one combination, and then, oh wait a second, there's a formula for that I can use, because I can just say, I'm gonna use the input example. Oh, why did I remove it? Damn it, maybe this is easier to wrap my hand around. Maybe not even this, maybe like this. Something smaller to work with, so I can just like be able to reason about it without getting overwhelmed with so many, with such a large input. So I'm gonna paste this in here, input example, and I'm gonna use this. So let's run again. What's our graph look like? Okay, so this is better. This is better. Okay, so we have, from 1, there's only one possible combination, so that's 4. And then 4 has 3 possible combinations, 5, 6, and 7. So you go to 5. 5 has 2, 6 only has 1, and 7 has 1. Can you somehow do like 1 plus wait, so 1 times 1 plus 3 times 1. How many combinations do we have in here? How many arrangements? Part 2 in here. 8 arrangements. There's 8 arrangements in here. So that's 1, 2, 3, 4, 5, 6, 7, 8. Is that it? Wait a second. So that's 1 at least. Like if you go to all of that, 1, 2, 3, 4, 5. No, you kind of like need to branch off. That's 1, and that's different branch. Oh, I'm sure there's a mathematical way to solve this pretty efficiently. So this is one combination, and then this one has 3 branches. So this one has 3, so 1, and then you can discard the first one, 2, and 3. And this one has another one as well. If you go into 5, so you can discard the first one, so it's like 1, 2, 3, 4. I'm not sure you can discard the first one though. 4, 5, 6, you go into 6, 7, so that's kind of like 1. So 4, 5, 6, 7 is the first one, and then 4, 5, 7 is the second one. And then 4, 6, 7, and then 4, 7. So how many do we have here? 4, 5, 6, 7, 4, 5, 7, 4, 6, 7, 4, 7. So that's 4 combinations here, and then for each of those, this one is a different combination as well. So oh, I see. Every branch, so I think it must be to the power of, and this is a fifth. Yeah, so 4, and then 4, that's 8. We have another one that branches off for each of them. Is 8 possible combinations. Trying to figure out. It might be possible to do some combinatorics from the graph data, but I'm too stupid for that. At least until I've written a program that never finishes. Yeah, I wonder if it's just gonna be easier to do. Because given this input, can we come up with some mathematical formula that just gives us 8? Because we have first combination is here. You just go through all the elements, all the first elements of those arrays, so like 4, 5, 6, 7, 10, 11, 12. That's the first one. And then the second one, we kind of like branch off into the second element of the first array, and then that's a second solution. And that's a third. But then for this one, you can also branch off in 2 different ways. So that's second, third, so that's fourth. And then fifth, if you branch off at 12. And then 7 has also, no it doesn't, because that's already 7. Oh, so you can't just, because 7 skips to this one. Okay, and that's 6, well 5. But then there's 2, let me think. 1. So we have 3 arrays that are, so we have 3 nodes that have multiple children. That's it. We have 3 nodes that have multiple children. And therefore, we need to kind of like start at the top, and then we can say for this child, there's X amount of the combinations, which is going to be 1. This one has 2 combinations. But then for each combination, there's another 2. So kind of like to the power of. So 2 to the power of, this one has 2 to the power of 2, 4. 2 to the power of 2, 4. And this one has 2 to the power of 1. So that's 2. 2 plus 4 is 6. And then we are in here, and this one has, let me see, 5, 6. Well, something I need to avoid is that, if I'm in here and I'm in 7, so I'm 4, 5, 7. This one has also 2, so that's 8. I might came up with a formula, at least in this case, the formula is right. Again, you loop until you find the first node that has multiple children, and then you count how many children like there are besides like the one that always there. So there's 2 extra children here, and then for so you take 2 times 2 to the power of, oh damn it, I got it there, but now I forgot it, because 6, so there's 2 children here, and then you say, okay, this one has 1, which means that those two children have each, well, at least if 7 is bigger than, oh no, that's okay. No, I'm gonna ditch the math idea. I'm gonna traverse the graph. This is not doable math. At least you'll have to traverse anyway, as far as I can tell. Okay. Traversing the graph, there we go. So I go into the graph, first element, well, first property. I'll need to kind of like count the possible arrangements. So I'll write a recursive function that will take the current element and the graph and kind of like tell us how many children it has, then for those children as well, and so on. But I need to remove not possible solutions though, because let's say so I have one goes to 4, and then 4 goes to 5, 6, and 7. So let's say it goes into 5, 5 goes into 6, into 7, we reach the end. Okay, so we reach the end, and then we can like keep up maybe a global variable state, like a variable that can count, like, okay, we reached 1, or we reached the end one time, and then go back, and then 12, go into 12, and then go to the end. If you reach the end, we can count it another, we have our second arrangement, okay? Then go back into 7, and then 7 is gonna go here, so we have our third, and then 7 is gonna go into 12 again. No, it's gonna go back and into 12, yeah, so then we have our fourth, and then go all the way back to 6, and 6 does the same thing. 6 jumps in here, 5, 6, and then go all the way back to 7, 7, 8. Okay, that's gonna work. Let's have arrangements. Let arrangements is 0, and then 4 const. So we have our object. We're gonna do for off, and then we can do, I'm sure we can do kind of like this. Adapter, children, adapters, for off graph. I'm just gonna add a simple console log in here so we can debug it. Something's wrong. Const for off. Oh wait, off is for erase, for in. Okay, let's try it again. So adapter is 1. Children adapters undefined. Okay, so that's not the spread for off. No, that's a weight off. Well, it doesn't really matter. For off here. So if I want to have the an array of, how do I do that? Key value, or maybe I just do object values. Object values is gonna return a two-dimensional array, and then I can just do for off, I guess. Let's see. Graph values. How about now? Oh wait, I need to use it on the object prototype. Object values. There we go. They should give us what we want. Adapter 4, children adapters, none. So for, oh no, that's not what I mean, not values, entries. There we go. Entries. From entries, yeah, that makes sense. Okay. Adapter 1, children. Okay, this is looking good. And then we need to keep in mind that the adapter is going to be a string. Do we care about that? No, not really. No, we don't care about that. We're not going to do any additions. Okay, so we have, and then for each child adapter, wait, I'm creating nested loops here, and I was talking about recursive functions before. For each child, could I use a nested loop? I'm just gonna give it a try, not sure. Children adapters. For child adapter, for children adapters, go into, what do we need to do here? So then we need to grab, oh yeah, okay, so we'll need to use a recursive function, yeah, because we're going to do the same thing. We're going to grab the adapter and the children adapters of that adapter, and then we need to loop through those. And so let's just create a function that count traverse graph. Yeah, that's good enough. And our traverse graph function is going to take the adapter as the first parameter, and the second parameter is going to be the actual graph. We can just, I guess it could be graph. Yeah. And then if let's grab the children adapters, graph adapter. If children adapters length, if there's no length, or if length is 0, then we means we reach the last adapter, so then we need to return 1. Return 1. If we do have a length, then it means if we do have 1, then for each one return children adapters. For each child adapter, traverse graph child adapter. And we don't need to pass it in the graph, because it's just going to use it from out of scope. So I guess that's all right. And here we need to add it. So we need to say, because it's going to return 1, and then we need to keep track of that 1. Let me see. We did it in a previous day. We kind of like did the same thing where I kind of forget my own solution. In another day, we traversed the graph and we summed kind of like the output. I think it was here. No, it's not this one. Number of banks. I think it was this one. Oh, we used the reduce. You use the reduce, and then I guess I could do that as well. Yeah. Get number of arrangements. Get number of arrangements. Okay, so it's going to return 1. And then here we need to use a reduce that let me see. That is going to be number of arrangements plus, I'm not sure if this math is entirely right. Don't even need to have the variable in here. You can just call get number of arrangements with the first adapter. So that's going to be graph 0. Okay. And let's call this answer part 2. I'm not going to run it yet because I'm sure it's not correct. Let me go through and see. So first adapter, does it have children? Did we reach the end? No, we did not. Therefore, go in here, and then for each child adapter, call this graph, traverse through it, and then number of arrangements, kind of like 0 plus. I'm just gonna run it. I'm curious what the output is. Length of undefined. Where is that? Oh, here, children adapters. Length of undefined. Which in which case is length undefined? Doesn't every Osmo graph look like? Let me run this. Graph looks like this. Every adapter has a child, doesn't it? Children adapters. Graph adapter. Where's our breaking point? Is it breakpoint? Where are we? We're here. No. Let me add a breakpoint in here. I want to figure out, what does it go to the end? Oh, because I have a breakpoint here, don't I? Yep. Okay. Run again. It doesn't. Oh, because it errors, of course. Here. Okay. So children adapters is undefined for some reason. Adapter is undefined because graph. Oh, it's not an array, of course. Graph first key property. It's gonna be Well, one thing is that let me think. I'm gonna declare assorted adapters here, and then I'm gonna put that in here because I'll need to reuse this. Sorted adapters and then map. There. I'll need to reuse sorted adapters to kind of like grab the first one and then the graph of it. Okay, let's run it again. We get 8. Awesome. That's interesting. I got the right answer right off the bat. I did not even went through the logic and made sure it's correct. I thought I was missing something, but maybe not. I'm gonna run it with the actual input. Let's see what we get. If the stream freezes because I got an infinite loop, sorry in advance. Now it says return 1 or just increase global variable arrangements, then there's nothing to keep track of. Yeah, exactly. Thanks. Yeah, I figured it out while here in the while doing the recursive function. Yeah, thanks for your suggestion. Length of undefined again. For some reason, I'm gonna add a breakpoint here. So we get undefined for our own input for some reason, but not for the example input. Let's run again and see what the sorted adapters is like. Why can't I? This is the graph. Global sorted. It's not in here. I wonder why sorted adapters is not. Is it because sort does not return a new array but changes it in place? And returns the sorted array. Okay, and returns the sorts are in place and returns them. So I guess adapters is already sorted because from the first part. So maybe I don't even need to. That's kind of like hacky. Let me move this up here. Sorted adapters. Or at least I know it's in place, so I can just. It returns the sorted array. Yeah, it's in place. So then we can just get rid of this. Oh, let me draw a new line. And then adapter sorted for the second part as well. And we got it in here. Length of undefined. Okay, let's run our debugger again. So now we have adapters is sorted. Well, oh, I see. I'm returning the children. So I'm already passing in the children, which I should or should not. Maybe. Do I need a parent adapter for anywhere. Children adapters. I don't really use the parent adapter because I get the oh, I do use it to get the children adapter in here. Yeah, so let me just do it like this. I have no idea how I got the right answer for the example input. Okay, so we're stuck here. It's running. It's taking a long time to run. I'm kind of afraid I'm gonna freeze my computer. Yeah, I'm gonna stop it. 13 seconds, it did not give us an answer. I'm gonna run it with the debugger and go through each. Okay, so adapter is 1, and then children adapters is 2, 3. Length is not, so then let's go in here. So then we have children adapters. Move that. Child adapters 2. Child adapter is 2. Number of arrangements 0. And you do number of arrangements plus whatever this returns, which is the child adapter. It goes in here. We grab the children. Okay, go next iteration. Let me put a breakpoint here. Adapter 3 has children 6. Okay, go on. Adapter 6 has children 7, 8, and 9. So our count is 0 now. Let's go until maybe it's correct. Maybe it just takes a long time. Yeah, maybe it's correct. Maybe it just takes a long time to go through them. While it does that, so I'm kind of like, I'm gonna add a console. So I see what's going on, kind of like get a glimpse of the program running. What do I want to log? I want to log the adapter. I want to log the children adapters. Wait, not in here. Let's log it in here. So I want to log the current tally, which is the number of arrangements. I want to log the current adapter we're at and its children. Okay, I'm gonna make this big and I'm gonna run it again. It seems to be stuck on an infinite loop here. Does it? Or maybe that just seems like it. So adapter, so number is, so something's happening with our accumulator. Or is it? No. Because it's gonna, No, I think the accumulator is kind of like nested within each branch. So it's going to be 0 for that branch, but then the total accumulator is going to be different. So let me just log the adapter and children. I have no idea what to log, like to make sense that it's going the right way. Okay, it's kind of like going to the end and then going back. And then children still don't. Let's go to the top. Oh, there's no top. So like how big's our input? 97. Oh wait, what's the largest? 158. 159. I think we have 159 here. 150. Do I remember correctly? Yeah, 159. Okay. So our last adapter, 159. that returns 1 because it has no children. So 158 kind of like goes. It seems that it's doing the right work. It reached the end and then it goes all the way to the top. Should I just let it run for a bit? But let's try and log something comprehensive. I don't know what to log. That's gonna make sense in this recursive. So it goes in. It's at the adapter. It goes back and forth. Maybe what I want to log is maybe this console log. I kind of like want to log this every time, so we can say number of arrangements is equal to this, and then number of arrangements going there, and then we use this for here. So that's kind of like what I want to log. Okay, let's do this. Okay, it's running. It looks like it's working. So as it goes through each adapter or each possible combination, it kind of returns how many combinations that branch has, and then it just adds them together. Okay, just gonna wait a bit and see. I have no idea how long it should take, even though console logging is expensive with respect to performance. Yeah, is it? I didn't knew that. Maybe I should remove the console log then. Maybe now that I know it's doing, it's not like in a loop or something. It's not in an infinite loop, because I can see it's different numbers every time. And I went through the code. I could remove the console log. Maybe wait just a little bit more. Yeah, let me remove the console log. Okay, I'm gonna run it. So while we wait for that, yeah, I could console log the mod, every mod 100 or so. I could do that, but I don't have. Yeah, I could do that, but then I'll have to figure out where mod 100 is, though. Not sure what mod of 100 of what. Of like, because I don't have access to. I don't know, within the function, I don't know how deep inside I am and on which branch I'm on, because I don't really know, don't really have access to that. I know which adapter I'm at, and I have its children. Yeah, I'm gonna let it run. Hopefully I get the correct answer within a considerable amount of time, because there's more than 1 trillion ways. If the accumulator is of global variable, then reduce is not needed. Yeah, that's true. I got rid of the accumulator in here because I could just like use reduce. I could refactor this into having an accumulator here, and instead of returning reduce, I just add to the accumulator. Perhaps that's faster. If like in terms of how many functions going to be in the call stack, and I think that's going to optimize our solution a little bit, because this takes quite a while. Yeah, I'm going to go with that. Thanks for suggesting that, Lars. I'm going to keep track of number of arrangements here, and that needs to be a let. And then this is just going to be traverse graph. and then in here return well, number of arrangements plus plus, return, yeah, just return, I guess. And then in here we say traverse graph child adapter, kind of like this. And what I can do is I can console log every 100. So I can say if number of arrangements mod was mod here, let's say 1,000 even, 1,000, then console log number of arrangements like this. Yeah, okay, let's run it. Child adapter is not defined because, okay, so we for each, and then there. Okay, so we're there, we're logging our tally at every 1,000, and it's doing a bunch of logging. Okay, there's gonna be trillions of them. I think let's do it at every 100,000. No, equals 0. Okay, there we go. So every 100,000 it's logging. Holy shit. Sorry, pardon my language there. I kind of got overwhelmed. It's running super fast. I'm gonna run it at every million. 100,000, 1 million, maybe every 100 million, 10 million. What is this? 10 million. Okay, this is better. Okay, so we're at 30 million, I think. No, we're at 500 million. We are reaching 1 billion or trillion combinations. But I think it's running much faster now without the nested, without the reduce. It looks like it's running much faster without the reduce. Because the reduce, it would just make it, yeah, it would add a, it's much more efficient to keep track of your state yourself than have a reduce function which calls another function, which then calls another function, and then you have multiple nested reduces, and then your stack is so much bigger and it's less efficient for the computer to run the program because the stack is so long than if you just have something like this. So we're 2.5 trillion or billion, I don't know what's called, combinations in, and it's still going. Yeah, as well, yeah. Reduce creates a closure for each edge. Exactly. So not only we have a very big call stack of functions, but each stack has its own scope, closure scope from the outside, which node needs to keep track of. So that also adds to the inefficiency of the program. Well, I'm still waiting here. We're like 3.6 billion multiple possible arrangements and we still haven't found our solution. I do hope I'm logging the final count so I don't have to run the program again. Oh, I do. Yeah, good. 4 trillion. I guess I've never done other events, Advent of Code events in the previous years. I've only done like the first 2 days of last year to prepare for this year. But I did hear that some days the solutions for some puzzles take a while to run. Like not hours, but on a relatively modern machine, some answers do take several minutes, up to like 10-15 minutes to run. So that might be one of those cases where, because we're doing brute force after all, we're not taking a mathematical approach to solving this, or combinatorial function or math equation, anything like that. We're just traversing the graph. We did make it more efficient by creating a graph and the way we're traversing it. So that's more efficient, but it's still going through each possible arrangement, which is a big O notation of n to the power of n, I think, which is huge. Or is it n squared? I think it's n to the n. 6 trillion in, still not there. What is the total number of distinct ways you can arrange the adapters to connect the charging outlet to your device? There must be more than 1 trillion valid ways to arrange them. How much is 1 trillion? Is that like 1,000 million? Because if that's the case, then we are nowhere near 1 million. No way. Trillion, 1 million. Because we're like million. We're like, where are we right now? 7 billion. It's like 7,000 million. So we're here. So it means that if there's at least 1 trillion different arrangements, then we're at 7. We have to go into 1,000 billions. Here we have the scale. We're at 7 billion. If there's 1 trillion combinations, then we have to go up to 1,000 billion, and we're only at 7.6 billion. That's gonna take a long time. No. If I get getting from the puzzle says you glance back down at your bag and try to remember why you brought so many adapters. There must be more than 1 trillion valid ways. And because more than 1 trillion is bolded, I think they kind of like hint us that there's indeed more than 1 trillion valid ways to do it. So going through them, the brute force approach is not gonna get us there. I'm afraid. Even though we were really smart in creating the graph and traversing it, it's just not efficient enough. You can't brute force this. You need to have a mathematical approach to solving this puzzle. And means we're back to square one. Surely there must be an efficient way to count the arrangements. I'm going through the graph. See, maybe I'm counting double. Am I counting things double? Because that would make it not efficient at all. But just there's so many different combinations here. Yeah, we're approaching 10 billion. It was fun though. Yeah, it was. Yeah, I'll need to solve this in a mathematical way, and we're already 2 hours and 10 minutes into the stream. We're back to square one with second part. If I have to restart the second part and find out what math problem, math equation I need to use, it's going to take me a long time. So I'm afraid I won't be able to finish this puzzle in the stream. I will go on off stream and try to solve it for today. And then when I have a solution, I will post it on the GitHub repository and on my Twitter account. So do add me on Twitter if you want to find out if I eventually solve this today or not. This is my Twitter account. Oh, this is not my Twitter account. This is my Twitter account. I'm gonna post it in the chat. And the repository where I'll eventually post the solution is in here as well. So let's go back. It's still going. Yeah, it's at 11 billion. And if there's indeed a trillion arrangements, this program is going to take a long time before we reach 1,000 billion, which is 1 trillion. Yeah. Unfortunately, doing this in a graph traversal way is not giving us the answer. Let me see if this looks right though. Return. Otherwise, for each traverse graph, yeah. So we stop the graph when we reach the end, the traversal. Then we go all the way back. Yeah, someone's at the door. I'm gonna stop the stream for today. Thank you guys for watching and keeping me support. Thank you, Lars, for trying to solve this with me. Too bad we couldn't do it. Keep an eye on my Twitter account and on the GitHub repository, and I'm gonna try and solve this later today, so then tomorrow we can continue with day 11, same time, 10 a.m. Central European time. Thank you very much, guys, and see you. Bye bye.